This is the lecture where we finally begin to talk about non-rigid bodies. This whole time we've been talking about rigid bodies, and we emphasized it with the rotational lectures because it's extra important. But lots of real-life objects bend and compress and stretch and deform enough that we just can't ignore it. So we're going to talk about 3 types of stresses and strains that an object can experience: tensile, bulk, and shear. The stress causes the strain. That's a good thing to remember. The stress causes the strain. Tensile stress causes tensile strain. Bulk stress causes bulk strain. And shear stress causes shear strain. And there's a law that characterizes the relationship between stress and strain for small stresses. And it's called Hooke's law. And you might say, hey, wait, we already saw that. That was with springs. Well, that was just one special case, one application of the more general Hooke's law. And so Hooke's law just says that the relationship between stress and strain for small enough stresses is that they are proportional to each other. So we have stress and strain down here. And they're related by some proportionality constant, which is called the elastic modulus. The elastic modulus. Well, this is Hooke's law in general, so I will write Hooke's law. So the reason it applied to springs is that the amount that a spring deforms is proportional to the force that's acting on it. So the stress was the force compressing it or expanding the spring, stretching it. And the strain is proportional to that. So that was Hooke's law applied to springs. Okay, so we're going to go through the 3 different types of stresses individually. The first one we'll talk about is tensile stress. So tensile stress and strain. Yeah, I'll just write tensile. So this comes from the word tension, right? So this is like a pulling force. So I'm going to write tension, pulling, right? So if you have a cable or a rope or a string, all kinds of things that we've dealt with Newton's second law, they were always providing a pulling force. You can't use a string and then push something, right? You're not using it in the same way, at least. And so, tensile stress is the stress of being stretched. Tensile stress is defined as the force that is perpendicular to the thing that it is pulling on. So F perpendicular to whatever area it is pulling on, divided by that area. So if we have like a cube, right, and there's some tension force here, and the perpendicular component of that tension force, tension perpendicular, that's kind of interesting. And then this is the cross-sectional area, and I'm going to rotate this around so you can see what the heck I'm doing here. All right. So that shows a tension that is perpendicular to that surface multiplied by the area. That is tensile stress. The SI unit of stress in general is the Pascal, named after some guy, right, as everything in physics. Pascal. Guy or girl, of course. And that's abbreviated PA. And that's equal to a Newton per meter squared. You might recognize that unit. It's the same unit as pressure. Same unit as pressure. So you can think of like pounds per square feet in your tires, your bicycle tires, or your per square inches, I guess, PSI. This would be a unit of pressure. It's the Pascal, and it's also the unit of stress. All right, so then let's talk about strain. So how do we define strain? Tensile strain is, so if this deforms a little bit, right? So we're saying that it deforms, so this object is going to stretch a little bit. Give it stretch marks. So it stretches a little bit. So it has some original length L, or it has some original length L that was, we'll say, here. And then it stretches to, that's L naught, and then it stretches to a length L, so just a little bit longer. Hopefully that makes sense. So it went from this length, and then we pulled on it, and it stretches a little bit to there, so it elongates a little bit. And so that L naught and L are important. So tensile strain is defined as L minus L naught, which is the amount that it stretches, divided by L naught per unit length, right? So the amount that it stretches per unit length. It's the fractional amount that it's changing. So we can write that as delta L over L naught. Okay, and then the elastic modulus, right? So there's stress divided by strain is equal to elastic modulus, right? So that's just the proportionality factor at which these two are related. So the elastic modulus for tensile stress has a special name. Don't know the history of why, but it's called Young's modulus. Young's modulus. And it's usually abbreviated with a Y. And it's stress over strain. And so the stress is this. I didn't write it out here. Stress was this one. That's tensile stress specifically. So we have F perpendicular over A divided by the strain, which is delta L over L naught. And so that would be F perpendicular over A multiplied by the inverse is L naught over delta L. And that's about as much as we can clear it up. So that is Young's modulus. All right, next one is bulk stress and bulk strain. Bulk stress is compressive stress. It's the opposite of tensile stress. Bulk stress is defined the same exact way, but the force is acting in the opposite direction. And another name for bulk stress is pressure. And so, put in a color here, why not? Bulk stress. Bulk stress and strain. And bulk stress is defined in the same way. It's just acting in the opposite direction. We call that pressure, P for pressure. You know, there's another P over here with Pascal, but this is P for pressure. It's a lowercase p, and it's F perpendicular over the area, again, but it's acting in the opposite direction. And bulk strain is defined in the same way as well, except for we're considering the volume instead of the length. And so strain, bulk strain is delta V divided by V naught. So it's the amount voluminously that it changes per unit volume. And so this is like, an example of this would be something that's underwater, deep underwater, and it's just being acted on all sides. And so if we have our cube here, and we brought it underwater, it would be experiencing pressure just everywhere, right? And so that's bulk stress. And so it's going to shrink voluminously. It's going to get smaller because of the pressure, right? And so we need to see the change in volume. So this would be like V naught, and then this would be V, and the difference in that volume defines this strain, the difference per unit volume. And so then the bulk modulus, the proportionality factor that relates to 2, is just stress over strain. And so the bulk modulus, I think it's capital B. Yeah, capital B is equal to, there's a minus sign, simply there because things are acting in the opposite way. It's crushing the thing instead of stretching the thing. So minus the change in pressure divided by delta V, V naught. Let me check that. Yeah, that's correct. So the amount of pressure change that happens, it causes a volume change. All right. The minus sign we talked about is because it's compressing things. And then before we move on to the last one, I wanted to say that there's some really fascinating things that come out of this, even though it doesn't maybe on its face seem as interesting as some other stuff we've been doing, at least to me. But really, the science of materials is fascinating. So there are certain materials that have unusual properties, and those just become inherently intriguing the more that you study this kind of thing. For example, most materials can withstand about the same amount of stretching as they can compressing. So the same amount of tensile stress as bulk stress. However, concrete can withstand great compressive stress, but it can fail under relatively weaker tensile stress. So this makes it ideal for some use cases, but a horrible choice for others. You can have many pounds of force resting on it, but if you try to pull it apart, it kind of is brittle and it pulls right apart. And the same property, the same thing is seen in stone. And that's why ancient civilizations that used stone as their building material had to design their doorways as arches so that the stress was all compressive and there wasn't any tensile stress going on. And so it really pervades all these different fields, architecture and history. It's the reason for a lot of things. Things can also experience multiple stresses at the same time. So if you lay a bar horizontally, let's say this is an iron bar, right? And it has some volume. It's not. It has some volume. Get this going here. It's pretty heavy, right? I say it's iron, and so if it's long and it's only supported on, let's say this end here, so there's something supporting it here. And there's something supporting it here, it can sag in the center. It can sag in the center, and it ends up sagging a little bit under its own weight. I'll just exaggerate it here. Right, a very exaggerated depiction. And when that happens, there's a top part here, this whole top surface is experiencing compressive forces, right? Because it's shortening in length, right? So there's compressive forces here on this top part, and there's stretching forces here. I don't know how to draw stretching forces, but it's stretching here. Let's do this. Stretching here, and it's compressing here. So it's experiencing both tensile stress here, and it's experiencing bulk stress there. Or at least compressive stress there. And so, consequently, the top of the beam needs reinforcement from the compressive stress up here. So you'd want this top part extra reinforced, right? Extra reinforced. And you want the bottom part extra reinforced so it doesn't break under the stretching force down there. In the middle of the beam needs no reinforcement at all. So there's some center line here. And the farther you get away from that center line in either upwards or downwards direction, you get more and more stress, right? So this layer is experiencing some compressive force, but not as much as the very top layer. And this layer is experiencing some stretchy force, but not as much as the bottom layer, right? And so, consequently, you don't need any reinforcement in the center because it's not experiencing any stress at all at that exact center line, right? But at the bottom, it's experiencing a lot. At the top, it's experiencing a lot. So we can even cut out the center part, or a lot of the center part, and just shave all this part out because it doesn't need any reinforcement there. Like this whole section here, we can cut out and just leave something in the center, and something reinforced up here, something reinforced up here, and this is all empty space, and this is all empty space. Do you see what we've arrived at? I don't know, maybe this is way too much of a mess for you to make sense of, because there's a lot overlapping here. But check out like the most common building unit, the I-beam. Right? Familiar with this thing, the I-beam? Look at the shape of that. It's almost exactly what we just discovered for what a material would need to resist compressive and stretching stresses on the material. You don't need anything in the middle part. You can cut it and save weight. But you need reinforcement here and you need reinforcement here, right? And it kind of tapers because the closer you get to the center line, the more reinforcement, or the less reinforcement you need. And so it's kind of interesting. You kind of start to figure out why things are the way they are. I always used to think that things were the way that this beam was the way that they are because the bolts, and you can see some bolts here. You know, I was thinking, well, it's convenient for these bolts to get bolted together if you have these like thin plates and everything, and I don't know what else. And that's true, but that's just that's an auxiliary benefit. It's really just like to save a ton of weight and a ton of material because we know where we need support and reinforcement, and we know where we don't because of the physics of it. So I thought that was really neat when I was learning this stuff. All right, so then the final one is shear stress, and that is what the sheep was all about in the beginning. The last type of stress is shear stress. The stress of having one part of the object pushed one way while the other part is pushed the opposite way. And this is my joke, right? Sheep get sheared. But you have stress on it this way on the bottom part and this way on the top part. And so you get this kind of shearing effect, I guess that's what the word is. And so the way that this is defined, move this up out of the way, and I'll switch to a new color since we're in a new topic, or a new type of stress. Shear, spelled differently. Oops. S-H-E-A-R instead of E-E-R. So shear stress is defined as F parallel over the area, and the area that we're talking about is if we have a box again, cube. Let's say it undergoes some shear stress and it becomes this thing. Right? And that's because there was some force this way, F, which is parallel to this area here. I can't rotate things this way, but maybe we can tell what I'm talking about. This area here is the area, and this force is acting parallel to that area. And so that's what we're defining there. And the shear stress, shear strain is defined as x over h, and of course I have to define what those things are, yeah? So h is the original height here, that's h, and x is, if you draw a line here, I'll use a different color to stand out, a line here to a line here, right? The amount that this thing shifted to the right, that's x. So it's the ratio of the height to the amount that that top area shifted. That's shear strain. And so therefore, the modulus, capital S, the shear elastic modulus, S, is equal to stress over strain. And so we have F parallel over area times the inverse of this guy, H over X. And that's that.